plate heats above 200 degrees C.
Look at the droplets. What do you think is going on, huh?
Interesting. The water starts acting in a rather bizarre way.
Has nothing to do with the Teflon or anything like that, huh?
Why isn't it evaporating?
Look at this. Look at the crazy droplets staying there. Right? Anyway, that had to have made you curious, right? Isn't that awesome? The guy who figured this out in 1700, right, was like, oh, magic, right? Of course. But so what's the story with this? It's a particular type of boiling, and we're going to get into that type of boiling in a second. So let's start by looking at some concepts. You see, we have for boiling. I'm going to talk first boiling. If we have time, we're going to talk about condensation. For boiling, what is happening is, first of all, we need an interface because it's a change of phase from liquid to gas. So we need a liquid-gas interface. And at that interface, we have a loss of mass from the liquid into the vapor. And as the mass is transferred, right, there's a latent heat, right? You knew this from week 2 when we were talking about energy balances and advection. And it takes the latent heat away. Now, when you account for all the subtleties of boiling, right, it's better than just trying to say something as easy as mass flow times latent heat. You just assign an H, a heat transfer coefficient, just as we have been doing with convection. Now, this phenomenon sometimes is related to a boundary layer, sometimes not. Doesn't matter. From the point of view of the math, all you care about is that you have Q double prime is H delta T. Now, the delta T, here's a trick. Remember, when we had convection, we said T at the surface minus T infinity, right? In this case, it's not going to be T infinity. It's going to be T of the phase change. For example, in the case of water, that would be 100 degrees, right? For water evaporating at boiling at atmospheric pressure, right? So you don't need to know what the temperature of the water is when you're boiling pasta. In this case, you're going to say T of the surface minus 100 degrees, right? Easy. So boiling, right, has similarities with what we have seen about convection. For example, you can have the equivalent of natural convection, right? That is in which the velocity of motion of the fluid comes from buoyancy, right? That is called pool boiling. Now, there is something that is similar to forced convection, right? That is, well, I put forced convection cooling anyway, yeah. But you can force it. For example, when you're boiling water inside the tube and you're pushing a flow through the tube. So that is according to the motion, similar to convection. Now, there is, according to the fluid temperature, 2 types of boiling. The one you see at the top is saturated boiling. That means the temperature of the liquid is slightly above the boiling temperature. For example, that's a typical case of water, boiling water for pasta, right? You have the bottom that is actually quite hot, and you generate a bubble, right? And this bubble is a bubble of water vapor. Now, this bubble reaches the surface. That's why you see this violent boiling, right? Now, the other type that is called subcooling is when you have a bottom really hot, right? But the top can be cold, right? For example, if you put something really, really hot inside a pot of water, but the pot of water was at room temperature, right? There is going to be boiling around. You can put heat up a bolt and nut until they're red hot. You toss them there, right? It's going to be boiling around them, right? But the water around is going to be colder. That's called subcooled. The main difference is this. If in the case of saturated boiling, the bubbles reach the surface, but in the subcooled one, the bubbles that are generated, then they get recondensed, right? Because there's no more free energy to have vapor. It goes cold. So let's talk about saturated pool boiling. So here you have a bottom, the solid, that is hot, and that's where the bubbles nucleate, and they raise up. If you look at a temperature profile, you're going to see that the bottom is hot, TS, surface temperature, like we have done so far, and then everything is slightly higher than the saturation temperature, not a whole lot higher. Right? This is the condition in which we're going to be looking at things. And there's a curve that I want to show you. This is a very important curve, and this curve is going to explain this Leidenfrost effect we have just seen in the video, which is pretty cool. So this curve, the horizontal axis, is excess temperature. So when we say an excess temperature of 30, right? What temperature does the water have? Or what temperature does the surface have? 130. The surface is 130, right? So 1 means 101, right? 1,000 means 100 and 1,000, 1,100, right? Okay, so the vertical axis is the heat flux, right? The Q double prime. So although we say Q double prime is H times delta T, this H is not so constant, right? So in this graph, what we see is something from which what the Q double prime is and what the delta T is. What do we see? That we can divide this in 4 clear regions, right? If you see the one between 1 and 5, right, it's pretty much a straight line. 5 and 30, it starts to go up. 30 and 120 goes down and then goes back up, right? Let's look at let's look at each of these sections in detail. Between an excess temperature, and this is for water at 1 atmosphere, other fluids behave similarly with different numbers. So between up to 5 degrees of excess temperature, so in the case of water at atmospheric pressure would be up to 105 degrees of the surface, what we have is that although there is an excess, buoyancy, natural convection takes care of things. So for the case of low excess temperatures, you use the same correlations we have discussed for natural convection. In particular, remember that we saw an equation for convection on the upward surface of a plate, right? And we also said you define the characteristic length as area over perimeter, so you can even have different shapes, right? So between 0 excess temperature and 5 degrees of excess temperature, you already know what you're doing. Now, things start getting interesting when we go a little bit higher. So if we go a little bit higher, okay. So when we go a little bit higher, what we see is we start to see these bubbles. As you see when you start boiling pasta, right? We see the bubbles. And at the beginning, you see isolated bubbles. And then you see more and more bubbles. And I have a video to show you of this. So I'll tell you the words, but I'll show you. And then more and more and more bubbles. And then the bubbles start to interfere with each other. And then they start to coalesce. So 2 small bubbles make 1 big bubble. And then depending on the geometry, you might have jets. You see in this image, you start having like a kind of jets going up. Or you can have like massive pulsating bubbles, right? But in this case, what is interesting is that these bubbles, as they go up, they cause motion of the fluid. And as you know, motion of the fluid is advection, and that enhances the transport properties. So in this graph, you see, I forgot to point out, but look at the numbers, right? 10 to the 3 is the smallest number. 10 to the 4, 10 to the 5, 10 to the 6. Right? So if we said air in stagnant air is 10, right? Forced water is 1,000, right? And here we're talking about 10,000 to 100,000. Something interesting about this, these numbers are so big, right? That these are the best way of cooling, systems that generate lots of heat. I was at a conference 1 or 2 years ago in the US in which they were discussing military lasers, right? When you want to shoot down a missile with a laser, right? As you know, lasers are super inefficient. So if you want to destroy a missile with a laser, you need a lot of energy. But lasers output about 1% of the energy they get. They're 99%, you just have to cool it out somehow. And so far, the best way of cooling these semiconductor lasers is you put in the back a heat sink, and you cool it in this regime of evaporation. You just shoot it with water that evaporates. That is the fastest cooling you can have. You don't have cooling channels. You don't have fans. You don't have any of that. You're just shooting it with this thing, right? Very interesting. You got to know what you're doing, right? And so in this case, the heat transfer is very enhanced. Look, it goes up by 2 orders of magnitude. It gets very, very, very intense. And then you reach this critical point, right? At the critical heat flux. Here's something interesting that happens. We've been looking at this curve as saying, oh, if I increase my excess temperature, right? And the curve makes sense to you. But in reality, you seldom do that. What you typically increase is the amount of heat you put into it. And this curve actually was first developed, and I'll show you the type of experiment they did, but by electrically heating a wire, right? So you know how much heat you put, and you can put more or less heat. When you do that, look at this. If I were to put in this experiment here 10 to the 4 watts per square meter, right? I would have something like, I don't know, 6 or 7, my excess temperature would be 6 or 7 degrees. You see that? Now, if I were to put 10 to the 5 watts per square meter, I would have an excess temperature of 10. If I were to put just 10 to the 6 watts per square meter, right, what would be my excess temperature? Something like that, right? Now, how about if I put say 2 times 10 to the 6? What is excess temperature? Yeah, I doubled the heat, right? I said 10 to the 6, you said 26 degrees, right? So the surface temperature would be 126, right? Now, I go double the power. I've been going by factors of 10, now I double it. What happens? 1,000 degrees. You melt things. So this was a paradoxical experiment because there was this guy in Japan doing the experiments and increasing the power little by little, and all of a sudden he would melt the wire. He would melt it again. Now this is the explanation, but he had to figure this out. And you reach the maximum amount of heat transfer. You cannot exchange more heat transfer than that at those low temperatures. If you want to do more, all of a sudden you jump like crazy to more than 1,000 degrees, right? Very interesting thing. Very important for everybody, because what this means is that, for example, if you're trying to boil water in a heat exchanger and you have flames, right? If you exceed if you put more fire than than the heat you can exchange in your boiler, you're going to end up melting the tubes, which, as a matter of fact, happens. Right? It's not that a little bit more, a little bit more, a little bit more, and you all of a sudden jump across this maximum. So this is a very, very important concept. The one take-home point of this whole class of today is this jump in surface temperature when you're about to exceed the maximum the heat flux, the critical heat flux. Here you go. This is an experiment this guy was doing in Japan. So he was putting this wire from end to end, kind of in a fishbowl, and running a current. So if you run a current, it generates heat, right? You know the voltage, you know the current, you're fine. And he was surveying this curve, right? And it melted. And the way he figured out this curve was by switching from a nichrome, that is nickel and chromium wire, to a platinum wire. Now, that's crazy. The guy was burning wires without knowing what was going on, and all of a sudden got a budget to put platinum wires. But he did, only in Japan, I guess. And the platinum wire could jump 1,000 degrees and did not get molten, because it goes from 1400 C to almost 1800, right? It had a lot more room for temperature. And then what he saw, once he could make the wire survive and not get destroyed, then he could start coming back down in this curve. Let's talk about this. So before I jump to the rightmost part, if we keep increasing the surface temperature, right, the saturation, the excess temperature, what we see is that the heat transfer starts going down. Now, that's a cute part of the curve, whatever we like. The book doesn't say, I've never seen any technological use for that part of the curve. Okay, so you have switches between nucleate bubbles and film, right? So I'm going quick over this part going down, which is a fact of life, but not really used. And now on the right, you have the minimum point, right? That is the Leidenfrost point. So if you look at that, it's very interesting, because at the very end of this heat transfer curve, you have a minimum of heat. So just think of this. A minimum of heat to some extent means that it's kind of insulating, right? What happens at that point is you generate a very thin film, right? And vapor has very low thermal conductivity compared with liquids, right? So this little film between the surface and the liquid creates an insulating layer. In this aspect, it's very similar to a boundary layer, right? When I mentioned between my arm and the air surrounding me, there is an invisible layer of stagnant air, right, through which we have conduction, and this is insulating. In that case, we have between the solid and the liquid, we have a thin layer of vapor that is acting as a boundary layer. Now, what I think is interesting about this is because it's the minimum heat exchange, that means you're not boiling too much of your droplet. And that's what you saw in this video of the Leidenfrost, how the droplets were moving and they were taking forever to evaporate, right? So at lower temperatures, for example, at 10 degrees excess temperature, right? If the surface was at 110 degrees, right? I'm exchanging a lot of heat, right? At point B. I'm evaporating things very quickly. But now, if the surface, instead of being at 110 degrees, is at 220 degrees, right? 120 plus the other 100. Now, actually, I exchange less heat. Isn't this interesting? So if the surface is hot enough at the right point, that's when you have this Leidenfrost effect, in which the droplets make this little film. And because it has this little film, it's like a hovercraft, right? It didn't look like it was Teflon or something, right? The droplets are just rolling free because they're supported by this cushion of vapor. And also, they're taking very long time to evaporate because this cushion of vapor is also to some extent insulating, right? So it's super interesting, super interesting. Now, from a technology point of view, all these things, you better know what you're doing, otherwise you're melting pipe, right? So you see in this image there that the bottom is the solid, then you have bubbles on top, and then in between the very bottom, that is the solid, and the bubbles, you see this film, right? And in this film, right, is relatively insulating. But of course, if you go crazy with the temperature, you're going to start conducting heat, right? But just by brute force. Something interesting here is between the hot surface of the plate and the temperature of the fluid, right? We have the film, but in a gas, we can transmit radiation, right? So radiation happens to be important in here. It's not only, if you were to calculate the heat exchange just based on the separation and the thermal conductivity of the gas, you actually should also account for the radiation between these two surfaces. Right? Very, very interesting. So let me show you this video. In the US. All right, guess where I'm not too sure we need all the music. We're not gonna do that in our videos. So what they are doing in the curve, they are making videos. The videos they are making are in this part here. So the first video is here, therefore. There you go. So you see, you still see bubbles, but they're coming together. And as they go, this is all the nucleate boiling. You have more and more. Okay. And now they are at this point, approaching the critical flux. Now you see how the bubbles are pretty much all together? So you're having a jet going up. I could watch this all day. I think it's awesome. By the way, I think we can do this in our lab. Chances are we have a better camera than them, and 2 of those. Right? I think so. The one really interesting one is when it is at the critical heat flux. Right? Look at this. Looks like a pulsating onion. Right? Isn't that awesome? So what I don't know why they don't show any more videos. Probably they destroyed their system. So now you realize that when you try to calculate heat transfer in this condition, it's quite complex, and the book has formulas. I don't care so much about those formulas as that you understand the concept, but everything here is super empirical. It's so hard to go get an equation from fundamentals of something that is being so chaotic. And in addition, when you have phase change, I don't know if in chemistry you talk about nucleation and growth, but the MADIs do, right? If you have solid and you have liquid, to have vapor, you have to create that. And that takes some amount of energy in the form of interface. So all these equations for boiling are affected by what is helping you or not helping you to create these bubbles. So you can, this curve we have here, you can move it. If you wanted to enhance boiling, there are special systems. In the book, they have a whole section in which you can have places that help you nucleate the bubbles, right? Again, all those are relative subtleties. What matters is you have this curve in which you have a behavior that is not intuitive. Everything I told you so far is for natural convection, right? It's for pool boiling. Now, for forced convection cooling, would be the case on a pipe, right? Of course, there are other ways, but the book discusses a pipe, and I think this is very appropriate. We can have external, not so much, to discuss, and internal. Let's look at this two-phase flow. Let's say we have a pipe. And let's say this pipe has this vertical flow. And as the liquid is flowing up, we're vaporizing the liquid. We're evaporating the liquid. So what do we know? We know this. At the beginning, we have liquid, and at the end, we have vapor. We all agree with this. Now, this curve on the right, is the heat transfer coefficient for different parts. So before we have any bubble, when it's all liquid, you know exactly what to do, right? And Nusselt is more or less 4, right? That is something that Ying taught when she taught internal flows. On top, when it's all vapor, same thing again. And the Nusselt number would be more or less 4. Now, in the middle, things get interesting. And of course, because when you have the two phases, the interaction between the two phases, the bubbles, help enhance the heat transfer coefficient. So, at the beginning, right, we have nucleation. And the water, if you look at the average temperature, is still below boiling, right? So this would be a subcooled boiling, right? You have some bubbles on the surface, but overall the liquid is not so hot. Now, we keep moving up, right, in our evaporator. So as we go up, we start to get saturated flow. By saturated means the average temperature of the flow would be 100 or 100 and little something. So we have these bubbles that now stay, right? In subcool, the bubbles can collapse because the vapor that makes the bubbles can recondense, right? And as we move up, we have these bubbles in saturated flow. Then we have what is called slug flow. And now is when you saw in the video how the bubbles would get together, they coalesce, and now they start moving like this big, like you don't want that in your veins, let's say, right? And funny, but you can in many ways. But you heard about the diver bands? Okay, when you're diving for a long time, right, you have nitrogen, it goes in solution because of the pressure, goes in solution in your blood. Now, if you remove the pressure all too quickly, the nitrogen wants to come out of solution, also known as boiling, right? That's what happens inside you. Now, when it reaches your brain, it's not too good, right? So it can go from painful to deadly. Now, because it's not a class in biology, but let's not destroy heat exchangers either, right? So now, but what you get to see is as we move up in the tube and we have more and more energetic ways of boiling, we start to have this bubble coalescence and moves up. Now, at the next stage, what happens is not anymore a bubble, right? And it's kind of funny how we went from a liquid that had some bubbles to just vapor that is surrounded by liquid, right? So we just have essentially a wet surface on the pipe, but we have vapor going inside. And at that point, especially when you get some dry spots, right? When you start to get some dry spots at the annular flow, right there you're reaching your maximum heat exchange rate. And at that maximum heat exchange rate is good. Again, like if you were to put too much heat, otherwise you might end up melting the pipe. The next step is whatever little liquid you had turns into a mist, right? And mist is also quite good at heat exchange, except that if you have too little mist, there is only so much heat it can take away. And when the mist disappears, when it's so hot now that you have no more liquid, you go to the full vapor phase, and heat exchange is quite reduced. Right? This is the way it works when you're evaporating things inside of the tube of a heat exchanger. Right. So we have discussed boiling and two types of boiling. We have discussed boiling in natural pool boiling, that is like natural convection, and forced convection cooling.